So in our previous lesson, we talked about adjacency matrix as a way to store and represent graph. And as we discussed and analyzed this data structure, we saw that it's very efficient in terms of time cost of operations. With this data structure, it costs big O of 1, that is constant time, to find if two nodes are connected or not. And it costs big O of V, where V is number of vertices, to find all nodes adjacent to a given node. But we also saw that adjacency matrix is not very efficient when it comes to space consumption. We consume space in order of square of number of vertices. In adjacency matrix representation, as you know, we store edges in a two-dimensional array or matrix of size V cross V, where V is number of vertices. In my example graph here, we have 8 vertices. That's why I have an 8 cross 8 matrix here. We are consuming 8 square, that is 64 units of space here. Now what's basically happening is that for each vertex, for each node, we have a row in this matrix where we are storing information about all its connections. This is the row for the 0th node, that is A. This is the row for the 1th node, that is B. This is for C, and we can go on like this. So each node has got a row, and a row is basically a one-dimensional array of size equal to number of vertices, that is V. And what exactly are we storing in a row? Let's just look at this first row in which we are storing connections of node A. This two-dimensional matrix or array that we have here is basically an array of one-dimensional arrays. So each row has to be a one-dimensional array. So how are we storing the connections of node A in these 8 cells in this one-dimensional array of size 8? A 0 in the 0th position means that there is no edge starting A and ending at 0th node, which again is A. An edge starting and ending at itself is called a self loop, and there is no self loop on A. A 1 in 1th position here means that there is an edge from A to 1th node, that is B. The way we are storing information here is that index or position in this one-dimensional array is being used to represent endpoint of an edge. For this complete row, for this complete one-dimensional array, start is always the same. It's always the 0th node, that is A. In general, in the adjacency matrix, row index represents the start point and column index represents the end point. Now here, when we are looking only at the first row, start is always A, and the indices 0, 1, 2, and so on are representing the endpoints. And the value at a particular index or position tells us whether we have an edge ending at that node or not. 1 here means that the edge exists. 0 would have meant that the edge does not exist. Now when we are storing information like this, if you can see, we are not just storing that B, C, and D are connected to A. We are also storing the not of it. We are also storing the information that A, E, F, G, and H are not connected to A. If we are storing what all nodes are connected, through that we can also deduce what all nodes are not connected. These zeros, in my opinion, are redundant information causing extra consumption of memory. Most real-world graphs are sparse, that is, number of connections is really small compared to total number of possible connections. So most often there would be too many zeros and very few ones. Think about it. Let's say we are trying to store connections in a social network like Facebook in an adjacency matrix, which would be the most impractical thing to do, in my opinion. But anyway, for the sake of argument, let's say we are trying to do it. Just to store connections of one user, I would have a row or one-dimensional matrix of size 10 to the power 9. On an average, in a social network, you would not have more than 1,000 friends. If I have 1,000 friends, then in the row used to store my connections, I would only have 1,000 ones, and rest, that is 10 to the power 9 minus 1,000, would be zeros. And I'm not trying to force you to agree, but just like me, if you also think that these zeros are storing redundant information and are extra consumption of memory, then even if we are storing these ones and zeros in just one byte as Boolean values, these many zeros here is almost 1 gigabyte of memory. Ones are just 1 kilobyte. So given this problem, let's try to do something different here. Let's just try to keep the information that these nodes are connected and get rid of the information that these nodes are not connected, because it can be inferred, it can be deduced. And there are a couple of ways in which we can do this. Here, to store connections of A, instead of using an array such that index represents endpoint of an edge and value at that particular index represents whether we have an edge ending there or not, we can simply keep a list of all the nodes to which we are connected. This is the list or set of nodes to which A is connected. We can represent this list either using the indices or using the actual names for the nodes. Let's just use indices because names can be long and may consume more memory. You can always look at the vertex list and find out the name in constant time. Now in a machine, we can store this set of nodes, which basically is a set of integers, in something as simple as an array. And this array, as you can see, is a different arrangement from our previous array. In our earlier arrangement, index was representing index of a node in the graph, and value was representing whether there was a connection to that node or not. Here, index does not represent anything, and the values are the actual indices of the nodes to which we are connected. Now, instead of using an array here to store this set of integers, we can also use a linked list. And why just array or linked list? I would argue that we can also use a tree here. In fact, a binary search tree is a good way to store a set of values. There are ways to keep a binary search tree balanced, and if you always keep a binary search tree balanced, you can perform search, insertion, and deletion, all three operations, in order of log of number of nodes. We will discuss cost of operations for any of these possible ways in some time. Right now, all I want to say is that there are a bunch of ways in which we can store connections of a node. For our example graph that we started with, instead of an adjacency matrix, we can try to do something like this. We are still storing the same information. We are still saying that 0th node is connected to 1th, 2th, and 3th node. 1th node is connected to 0th, 4th, and 5th node. 2th node is connected to 0th and 6th node, and so on. But we are consuming a lot less memory here. Programmatically, this adjacency matrix here is just a two-dimensional array of size 8 cross 8. So we are consuming 64 units of space in total. But this structure in right does not have all the rows of same size. How do you think we can create such a structure programmatically? Well, it depends. In C or C++, if you understand pointers, then we can create an array of pointers of size 8, and each pointer can point to a one-dimensional array of different size. 0th pointer can point to an array of size 3 because 0th node has 3 connections and we need an array of size 3. 1th pointer can point to an array of size 3 because 1th node also has 3 connections. 2th node, however, has only 2 connections. So 2th pointer should point to an array of size 2. And we can go on like this. The 7th node has 4 connections. So 7th pointer should point to an array of size 4. If you do not understand any of this pointer thing that I'm doing right now, you can refer to mycodeschool's lesson titled Pointers and Arrays, the link to which you can find in the description of this video. But think about it. The basic idea is that each row can be a one-dimensional array of different size. And you can implement this with whatever tools you have in your favorite programming language. Now let's quickly see what are the pros and cons of this structure in the right in comparison to the matrix in the left. We are definitely consuming less memory with the structure in right. With adjacency matrix, our space consumption is proportional to square of number of vertices. While with this second structure, space consumption is proportional to number of edges. And we know that most real-world graphs are sparse. That is, the number of edges is really small in comparison to square of number of vertices. Square of number of vertices is basically total number of possible edges. And for us to reach this number, every node should be connected to every other node. In most graphs, a node is connected to few other nodes and not all other nodes. In this second structure, we are avoiding this typical problem of too much space consumption in an adjacency matrix by only keeping the ones and getting rid of the redundant zeros. Here, for an undirected graph like this one, we would consume exactly 2 into number of edges units of memory. And for a directed graph, we would consume exactly E, that is number of edges units of memory. But all in all, space consumption will be proportional to number of edges. Or in other words, space complexity would be big O of E. So the second structure is definitely better in terms of space consumption. But let's now also try to compare these two structures for time cost of operations. What do you think would be the time cost of finding if two nodes are connected or not? We know that it's constant time, or big O of 1 for an adjacency matrix, because if we know the start and end point, we know the cell in which to look for 0 or 1. But in the second structure, we cannot do this. We will have to scan through a row. So if I ask you something like, can you tell me if there is a connection from node 0 to 7, then you will have to scan this 0th row. You will have to perform a linear search on this 0th row to find 7. Right now, all the rows in this structure are sorted. You can argue that I can keep all the rows sorted and then I can perform a binary search, which would be a lot less costlier. That's fine, but if you just perform a linear search, then in worst case we can have exactly V, that is number of vertices, cells in a row. So if we perform a linear search, in worst case we will take time proportional to number of vertices. And of course the time cost would be big O of log V if we would perform a binary search. Logarithmic runtimes are really good, but to get this here, we always need to keep our rows sorted. Keeping an array always sorted is costly in other ways, and I'll come back to it later. For now, let's just say that this would cost us big O of V. Now, what do you think would be the time cost of finding all nodes adjacent to a given node? That is, finding all neighbors of a node. Well, even in case of adjacency matrix, we now have to scan a complete row. So it would be big O of V for the matrix, as well as this second structure here. Because here also, in worst case, we can have v cells in a row, equivalent to having all ones in a row in an adjacency matrix. When we try to see the time cost of an operation, we mostly analyze the worst case. So for this operation, we are big O of v for both. So this is the picture that we are getting. Looks like we are saving some space with this second structure, but we are not saving much on time. Well, I would still argue that it's not true. When we analyze time complexity, we mostly analyze it for the worst case. But what if we already know that we are not going to hit the worst case? If we can go back to our previous assumption that we are dealing with a sparse graph, that we are dealing with a graph in which a node would be connected to few other nodes and not all other nodes, then this second structure will definitely save us time. Things would look better once again if we would analyze them in context of a social network. I'll set some assumptions. Let's say we have 1 billion users in our social network, and the maximum number of friends that anybody has is 10,000. And let's also assume computational power of our machine. Let's say our machine or system can scan or read 10 to the power 6 cells in a second. And this is a reasonable assumption because machines often execute a couple of millions instructions per second. Now, what would be the actual cost of finding all nodes adjacent to a given node in adjacency matrix? Well, we will have to scan a complete row in the matrix. That would be 10 to the power 9 cells, because in a matrix we would always have cells equal to number of vertices. And if we would divide this by 1 million, we would get the time in seconds. To scan a row of 10 to the power 9 cells, we would take 1000 seconds, which is also 16.66 minutes. This is unreasonably high. But with the second structure, maximum number of cells in a row would be 10,000, because the number of cells would exactly be equal to number of connections. And this is the maximum number of friends or connections a person in the network has. So here we would take 10 to the power 4 upon 10 to the power 6, that is 10 to the power minus 2 seconds, which is equal to 10 milliseconds. 10 milliseconds is not unreasonable. Now let's try to deduce the cost for the second operation, finding if two nodes are connected or not. In case of adjacency matrix, we would know exactly what cell to read. We would know the memory location of that specific cell, and reading that one cell would cost us 1 upon 10 to the power 6 seconds, which is 1 microsecond. In the second structure, we would not know the exact cell. We will have to scan a row. So once again, maximum time taken would be 10 milliseconds, just like finding adjacent nodes. So now, given this analysis, if you would have to design a social network, what structure would you choose? No-brainer, isn't it? Machine cannot make a user wait for 16 minutes. Would you ever use such a system? Milliseconds is fine, but minutes, it's just too much. So now we know that for most real-world graphs, this second structure is better because it saves us space as well as time. Remember, I'm saying most and not all, because for this logic to be true, for my reasoning to be valid, graph has to be sparse. Number of edges has to be significantly lesser than square of number of vertices. So now, having analyzed space consumption and time cost of at least two most frequently performed operations, looks like this second structure would be better for most graphs. Well, there can be a bunch of operations in a graph, and we should account for all kinds of operations. So before making up my mind, I would analyze cost of few more operations. What if after storing this example graph in computer's memory in any of these structures, we decide to add a new edge? Let's say we got a new connection in the graph from A to G. Then how do you think we can store this new information, this new edge, in both these structures? The idea here is to assess that once the structures are created in computer's memory, how would we do if the graph changes? How would we do if a node or edge is inserted or deleted? If a new edge is inserted in case of an adjacency matrix, we just need to go to a specific cell and flip the 0 at that cell to 1. In this case, we would go to 0th row and 6th column and overwrite it with value 1. And if it was a deletion, then we would go to a specific cell and make the 1 0. Now how about this second structure? How would you do it here? We need to add a 6 in the first row. And if you have followed this series on data structures, then you know that it's not possible to dynamically increase size of an existing array. This would not be so straightforward. We will have to create a new array of size 4 for the 0th row. Then we will have to copy content of the old array, write the new value, and then wipe off the old one from the memory. It's tricky implementing a dynamic or changing list using arrays. This creation of new array and copying of old data is costly. And this is the precise reason why we often use another data structure to store dynamic or changing lists. And this another data structure is linked list. So why not use a linked list? Why can't each row be a linked list? Something like this. Logically, we still have a list here, but concrete implementation wise, we are no more using an array that we need to change dynamically. We are using a linked list. It's a lot easier to do insertions and deletions in a linked list. Now, programmatically, to create this kind of structure in computer's memory, we need to create a linked list for each node to store its neighbors. So what we can do is we can create an array of pointers, just like what we had done when we were using arrays. The only difference would be that this time each of these pointers would point to head of a linked list. That would be a node. I have defined node of a linked list here. Node of a linked list would have two fields, one to store data and another to store address of the next node. A0 would be a pointer to head or first node of linked list for A. A1 would be a pointer to head of linked list for B. And we will go on like A2 for C, A3 for D, and so on. Actually, I have drawn the linked lists here in the left, but I have not drawn the array of pointers. Let's say this is my array of pointers. Now A0 here, this one, is a pointer to node, and it points to the head of linked list containing the neighbors of A. Let's assume that head of linked list for A has address 400. So in A0, we would have 400. It's really important to understand what is what here in this structure. This one, A0, is a pointer to node, and all a pointer does is store an address or reference. This one is a node, and it has two fields, one to store data and another a pointer to node to store the address of next node. Let's assume that the address of next node in this first linked list is 450. Then we should have 450 here. And if the next one is at, let's say, 500, then we should have 500 in address part of the second node. The address in last one would be 0 or null. Now this kind of structure in which we store information about neighbors of a node in a linked list is what we typically call an adjacency list. What I have here is an adjacency list for an undirected, unweighted graph. To store a weighted graph in an adjacency list, I would have one more field in node to store weight. I have written some random weights next to the edges in this graph, and to store this extra information, I have added one extra field in node, both in logical structure and the code. Alright, now finally, with this particular structure that we are calling adjacency list, we should be fine with space consumption. Space consumed will be proportional to number of edges and not to square of number of vertices. Most graphs are sparse and number of edges in most cases is significantly lesser than square of number of vertices. Ideally, for space complexity, I should say big O of number of edges plus number of vertices, because storing vertices will also consume some memory. But if we can assume that number of vertices will be significantly lesser in comparison to number of edges, then we can simply say big O of number of edges. But it's always good if we do the counting right. Now for time cost of operations, the argument that we were earlier making using a sparse graph like social network is still true. Adjacency list would overall be better than adjacency matrix. Finally, let's come back to the question, how flexible are we with this structure if we need to add a new connection or delete an existing connection? And is there any way we can improve upon it? Well, I'll leave this for you to think, but I'll give you a hint. What if instead of using a linked list to store information about all the neighbors, we use a binary search tree? Do you think we would do better for some of these operations? I think we would do better because the time cost for searching, inserting, and deleting a neighbor would reduce. With this thought, I'll sign off. This is it for this lesson. Thanks for watching.